First lecture over chapter 4. So this chapter covers what are known as free radicals and some of the reactions they undergo, and it looks at reactions of alkanes. Okay, so first of all, we'll start by looking at the stability of free radicals. What is a free radical and how stable they are? So a free radical is any species that contains an unpaired electron. So they're generally very unstable and very reactive. It is possible to have some free radicals are stable, but most are very unstable. So an example would be like this, where you have a carbon with 3 bonds and then 1 unpaired electron. So that would be free radical. So there are other reactive, so usually free radicals are intermediates in reactions. So there's other reactive intermediates. So you could have a carbon with only 6 electrons on it. So if we calculated the formal charge on carbon, for example, 4 valence minus 3 lines minus 0 unpaired electrons, it would be +1 charged. So carbon with a positive charge is what's known as a carbocation or a carbonium ion. Or you can have a carbon with 3 bonds and a lone pair of electrons, and if we calculated the formal charge here, carbon's got 4 valence minus 3 bonds minus 2 unpaired electrons, so -1 charge. So that would be what's known as a carbanion. So we'll look at carbocations and carbanions in other chapters. In this chapter, we focus on free radicals. And so, yeah, in this case, then the charge on carbon is 0, right? 4 valence minus 3 bonds minus 1 unpaired electron, so no charge. But it is a very reactive species generally. Okay, so let's look at how to classify free radicals. So when I say classify, I mean like primary, secondary, tertiary, methyl, allylic, vinyl, aryl, or benzylic. I spelled that wrong, B-N-Z, or some combination of that. So you classify free radicals just like we classified alkyl halides and alcohols. So the radical is on that carbon. How many carbons are attached to that carbon? So 1, 2, 3. So that would be a tertiary free radical. And radicals on that carbon has 1, 2 carbons attached to it. So that would be a secondary free radical. And radical is on this carbon. It has 1 carbon attached to it. So that would be a primary free radical. And in this case, the radical is on that carbon and it has no carbons attached to it. So that would be a methyl free radical. And then for the others, then the others introduce these concepts, allylic, vinyl, aryl, or benzylic. So since the radical is on that carbon, which is adjacent to a carbon-carbon double bond, it is allylic. And that carbon also has 2 carbons attached to it. So one of the carbons attached to it is part of a double bond. That's how you know it's allylic as well. So 2 carbons attached to that carbon, so it's secondary and allylic. In this one, so the radical is directly on a carbon-carbon double bond, so it would be vinyl. And that carbon has 2 carbons attached to it, so it would be secondary and vinyl. So this one, the radical is directly on a benzene ring, so it's aryl, and all aryl radicals would be secondary, right? Because that carbon with the radical has 2 carbons attached to it, so it's going to be secondary. Okay, so in this case, that radical is next to a benzene ring, so it's benzylic, and that carbon with the radical on it has 1, 2, 3 carbons attached to it, or one of the carbons attached to it is a benzene ring, so that is going to, so it's going to be tertiary and benzylic. Okay, so this last one, so how would you classify this free radical? So the radical, so if you keep in mind that is a carbon at the end of the line, right? It's not a CH3 in this case because it's missing one of its hydrogens. So that carbon, if we drew it out, has 2 hydrogens attached to it. and that carbon has one other carbon attached to it, so that would be a primary free radical. Okay, so if we wanted to know which of these are more stable, one way to look at the stabilities of free radicals or to figure it out experimentally is determine the bond association energies, or BDE. So through the homolytic cleavage of a carbon-hydrogen bond. So if we took methane, for example, and we cleaved one of these CH bonds, right? So each carbon takes its electron back. Talk about arrows. Where do I have arrows at? Oh, here we go. So notice the use of single-headed arrows. So a single-headed arrow means removing one electron each way, right? So single-headed arrow. So anytime you're working with free radicals, you're going to be using single-headed arrows if you want to show what's going on in the reaction, show how electrons are moving. So basically this means that hydrogen is taking one of the electrons in the CH bond, and that carbon is taking one of the electrons. So C and H take one electron each from the bond. So then you would have CH3 now with an unpaired electron on carbon, and you would have a hydrogen with its electron back. So homolytic cleavage means you break the bond and each atom in the bond takes its electron back. So if we look at the bond association energy to do this, that would be 435 kilojoules of energy are needed to break the CH bond in 1 mole of CH, in 1 mole of CH4 molecules. And then you would make a methyl free radical. So if we did the same thing for ethane, so if we break any of these CH bonds, so carbon takes its electron back, and hydrogen takes its electron back, and so the energy associated with that process is 410 kilojoules per mole. And in this case, you made a primary free radical. Okay, so if we did the same thing for propane, so if we take the middle carbon and we break one of its CH bonds, and then the energy is, so in this case now you make a secondary free radical. So the energy associated with that is 397 kilojoules per mole. And then if we have a tertiary center, right, that's a tertiary carbon. So if we break that bond and each atom takes its electron back, so notice the arrow starts on the bond because we're talking about those two electrons, and a single-headed arrow towards the top towards hydrogen. So hydrogen's taking that electron, and the other single-headed arrow goes to the carbon, so that carbon's taking the other electron. And you would make that. And so now you have a tertiary free radical. And the energy associated with that is 380 kilojoules per mole. Okay, so what does the energy difference means? So the lesser the energy to break the bond means it's a weaker bond, and that means that it leads to a more stable radical. So it took the least amount of energy to break the CH bond on a tertiary center. So that means that CH bond is the weakest, and that means the tertiary free radical is the most stable. So it's easiest to make. So it requires the least amount of energy to make. Whereas for CH4, that required the most amount of energy to break that bond. What that means is that's the least stable. So the methyl radical is the least stable. It's the hardest to make, so it's going to require the most amount of energy to break that CH bond to make it. So then, so in terms of stability of radicals, tertiary is more stable than secondary, which is more stable than primary, which is more stable than methyl. Okay, so let's practice a little bit. So let's classify each of these free radicals as primary, secondary, tertiary, methyl, or if it's allylic, benzylic, vinyl, or aryl, throw that in as well. So this first radical, so that carbon's got, with the radicals, got 3 carbons attached to it, so it's tertiary. So you could pause this video and you could try these right quick, see if you can classify each of those free radicals, and then restart the video and see if you got the answer correct. Okay, so for this next one, the radical carbon has 2 carbons attached to it, so it would be secondary. And in this one, so the radical is on that carbon, and that carbon is attached to this carbon and that carbon, so that's a secondary free radical. Okay, so for this structure in the brackets, I did not clearly depict which carbon has the radical, but you can figure it out based on which carbon does not have enough bonds to it. Right, that carbon's got 4 bonds, it's got 3 hydrogens, plus it's bonded to this carbon. And that carbon has 2 hydrogens on it, plus it's bonded to that carbon and to this carbon. And that carbon has no hydrogens on it, it's bonded to this carbon and these 2 carbons. So that carbon only has 3 things attached to it, so that must be where the radical is at. So that radical is really on this carbon. And so that carbon has 3 carbons attached to it, so that would be a tertiary free radical. Okay, so for this next one, so it's only got 1 carbon attached to it, and the carbon attached to it is not a double bond, so it's not in the allylic position. So this is just a primary free radical, right? To be allylic, it would have to be on that carbon because then it would be next to a double bond. So this next one has 2 carbons attached to it, and one of those carbons is a carbon-carbon double part of a double bond, so that's going to be allylic. So it's going to be secondary and allylic. And this one, the radical is directly on a carbon-carbon double bond, so it's vinyl. And that carbon-carbon double bond, or that radical carbon has 2 carbons attached to it, so it's secondary and vinyl. And for this one, so it's got that carbon attached and that carbon attached, so it's secondary. And since one of those carbons is the benzene ring, then it's also benzylic. Okay, so now let's practice stability. Which of these radicals is the most stable? So for each pair, circle the one that's more stable. So what you would need to do is classify them. So this is secondary, right? Because it's got 2 carbons attached, and this is primary. So secondary is more stable, so that's the most stable radical. So you could do the same thing. You could pause this video, see if you can circle the more stable radical, and then restart and see if you got it right. See if you understood this concept or not. Okay, so for B, this radical, so classify it. So the radical is on that carbon, and that carbon only has that carbon attached to it. So this is primary and allylic, since the carbon that you circled is part of a double bond. And this one has those 2 carbons attached, so it's secondary. And one of the carbons that you circled is a double bond, so it's allylic. It's 1 carbon away from a double bond. So the more stable, so allylic is a wash, they're both allylic, but this one's secondary, so that's more stable. Okay, so for C, so let's classify. So that radical carbon has 2 carbons attached, so it's secondary. And one of the carbons you circled is a benzene ring, so it's secondary and benzylic. And for the one on the right, that carbon has 3 carbons attached to it, so it's just tertiary. So which is more stable? Well, based on that, you might want to say tertiary, but as we'll see in the next concept that I show you, benzylic is better than tertiary, so that's the more stable radical. And for this one, so that carbon has 2 carbons, so the radical carbon has 2 carbons attached to it, so it's secondary. One of the carbons you circled is a double bond, so it's secondary and allylic. And this radical is just tertiary. And so same as C, allylic is also better than tertiary. Okay, so the real order of stability is benzylic is better than allylic, which is better than tertiary, and then secondary, and then primary, and then methyl, and those are better than vinyl and arrow, which are the least stable places to put a free radical. Okay, so lastly in this lecture, so why is allylic and benzylic the best? So if we take this free radical, it's a allylic position, right? So this is secondary and allylic. So we can draw resonance structures. So we can delocalize that. So this is an unpaired electron. So if you remember what resonance is, it's moving electrons through a pi system. So since it's in the allylic position, the radical is close enough in space to the double bond that it can delocalize through that double bond. So the way to illustrate this is we're going to take that and move it to make a double bond between the second and third carbon. And we're going to take one of those electrons in the double bond and move it over. So we're going to now our double bond is going to be between carbon 2 and carbon 3. And the other electron in the double bond we're going to leave behind on that carbon. So if you notice, we always split the double bond. One electron goes one way and the other goes the other way. Single-headed arrow because we're moving one electron at a time. And double-headed arrow here because that's what means resonance, right? So now our picture looks like this for the molecule. Now the double bond is there, and now the first carbon has the unpaired electron. Okay, so what does this look like in terms of the orbitals of the pi system? So if you remember, the double bond means each of these carbons has a p orbital. And in terms of the radical is sp2 hybridized as well. So we have a radical there. And the pi system, we're letting those two p orbitals overlap to make a double bond because they're on adjacent carbons. But if you notice, the radical is also adjacent to another p orbital. And basically what that means then is that this electron is free to go there, and this electron, nope, sorry, we don't need to move electrons at all. It just means that we could choose to do this. So each of these has one electron in it. We could choose to let those two overlap instead to make a double bond. And then now that's an unpaired electron, which is that picture, right? We have an unpaired electron on the end, and we have a pi bond between those two carbons. So the unpaired electron density can be shared between two different carbons, and that stabilizes the electron. And so that would be why allylic is better than, more stable than tertiary. And if it's in a benzylic position, so each of the carbons in a benzene ring has a pi bond to it. So each of those carbons has a p orbital, and the radical is in a p orbital. So each of the carbons in benzene has one electron in their p orbital. So right now we're letting these p orbitals, in terms of this picture, we're letting those two p orbitals overlap, these two p orbitals overlap, and those two overlap to make the pi bonds. But since the radical is on a carbon that's adjacent, these can overlap as well. So basically what that means is that unpaired electron can be on some of the ring carbons as well. And if we wanted to show that by resonance, we would move this electron there, that electron there, and move that electron to the other carbon. So now we'd have a double bond between those two carbons, and this carbon would have an unpaired electron, and we didn't touch the other two double bonds yet. So we could draw more resonance structures, so let's just keep moving that electron the same way around the ring. So move it down to make a double bond, move one of these back to make a double bond with the unpaired electron, and move the other up onto the carbon atom to make so that's where the radical would reside then. So now our double bond is between those two carbons. We did not touch the other double bond, so it's still there, and now the unpaired electron is on that carbon. And then if we draw another resonance structure, so keep going, so it's still allylic. So basically that unpaired electron is allylic to 3 double bonds. So we moved it to the first one to get to this. We moved it to the second double bond to get to that. Now we're going to move it through the third double bond. So bring that down, bring one of these over, and move one of these up. Okay, so that double bond is still there. Now there's a double bond there, and now the unpaired electron is there. So if you notice, the radical skips positions. It goes, so it started there, and then we skipped that carbon, and then it ended up there. And the same with the next resonance structure. It started there, and then we skipped that spot, and then it ended up there. Okay, so one more resonance structure we could draw. Whoops, let's keep that. So we can move this down. Whoops, single-headed arrow. We can move one of the pi electrons over, and the other one stays behind. Okay, so now our double bonds, yes. Oops, sorry, this double bond is not there. Now the radical's back to where it started at. This is another resonance structure, so there's 5 resonance structures. So this is not quite the same as where we started at, because the difference there is those two are resonance structures of each other as well. The double bonds have been shifted, right? So if we move that there and that there, and if you notice now I'm using double-headed arrow because now I'm moving 2 electrons in the same direction. So if we shuffle the double bonds in benzene, then we get back to where we started at. So for that benzylic free radical, it has 1, 2, 3, 4, that unpaired electron, can be on 4 different carbons. And there's 5 different resonance structures total, but one of them just shuffles the double bond. 4 of them moves the radical around. So the more that you can move that radical around to different carbons, the more stable it is. And so the easier it is to form. So that's where you get this order of stability for free radicals at. Benzylic is always the best, then allylic, tertiary, secondary, primary, methyl, vinyl, and aryl is the worst. Okay, that's it.